Christoph, and thank you all for coming to this talk and listening to the topic of quiet charging in the megawatt range for electric trucks. I couldn't have thought of a better introduction than the talk of Stefan Heuer, but I will still give you a quick introduction of where I see electric trends, electric trucks currently. So you have pretty strict EU CO2 targets, pretty ambitious as always. But they want to have a reduction of 45% at 2030 in the CO2 emission of electric trucks. So what we've also already seen from MAN and also all the other OEMs of trucks, they're all announcing their battery electric trucks. And what is now really coming up is the long-haul battery electric trucks. And what I find really interesting that even apart from all the environmental discussions that we have and that are important for the logistic companies, there's actually a pretty solid business case with lower total cost of ownership, especially for the long-haul vehicles, because they are more expensive when you buy them. They're about double as expensive or even 3 times sometimes as the combustion engine comparables, but they are much cheaper to operate in the operating range. So actually you want to have these vehicles on the road all time, driving long distances. So that's why the long range trucks are actually a good option for everyone. And of course, we are an acoustics conference. Stefan Heuer has already shown that they are, while driving, much quieter. So as an acoustician and also as a citizen, I'm all for it. Go for battery electric trucks. But as Mr. Heuer also mentioned, you still have this missing infrastructure. And this was actually part of the project we were involved in, where we looked into this megawatt charging infrastructure. So currently the estimates say that we need around 1,000 of these stations. There's a new charging standard being developed. You might know the CCS standard from the automotive industry. And now there's the MCS standard coming up. That's the megawatt charging standard for battery electric trucks. And that would allow charging up to 3 megawatts. So you can expect these to come up in the future, like every 60 kilometers or so on the Autobahn. And we did some measurements on currently available electric trucks to do the acoustic simulation, both for the outside and also look into the inside. So as Stefan Heuer also mentioned, the drivers have to do a break of 45 minutes after 4.5 hours of driving anyway. And there's no problem charging. You will have driven about 400 kilometers at that time. And you would want to get the battery filled up within like half an hour or so during that time, and the driver can rest. So we did some measurements. And what we found is actually this. So this was a microphone measurement taken 1 meter in front of the truck while charging. And don't be scared, I'll play back the sound. Thank you for toning it down. I hope you're awake now. So this is what the truck sounded like during charging. And yeah, this of course got us thinking, okay, how are we going to handle this in the future, both for the outside noise at these charging stations and also for the drivers. And what you heard was mainly the cooling system, because when you're charging the battery, you have a lot of heat created, and then at a certain point you need to start cooling the battery such that the chemistry of the batteries doesn't deteriorate. Are we on a ship? Is it moving up and down? Okay, so that was my introduction, but now we want to look into the charging noise a bit deeper. So first of all, I'm going to explain you the measurements that we did in a bit more detail, and we'll look into it and look at the different sources, part of what you just heard. And then we also did a simulation for the exterior noise at one of these charging stations that you would have next to the highways, and we'll look into that. And then we'll also do a small investigation into the interior noise in the truck, where the driver would ideally have his resting conditions. And finally, I want to conclude also with some recommendations, because this yeah, acoustic issue is absolutely technically solvable. I guess the main purpose of my talk is to just bring this into attention, that this needs to be considered in the development phase. Good. So let's look into the measurements. We had a, let's say, urban truck, which were available middle of this year. And during summer, we did the testing. So it had a capacity of around 350 kilowatt hours. We drove it around on the highway to get the battery empty, below 20% state of charge. And then we went to a charging station in an industrial area, and we charged it with only, quote unquote, 100 kilowatt. And what we found is that due to the battery temperature after driving, you first had only the fans of the dispenser running. So this was a measurement between the charging dispenser and the truck. And for the first couple of seconds, you would only hear the fans of the charging dispenser. So that sounds a bit like that. So you hear the fan running, you hear a little bit of the high-pitched noise from the inverter. And then after that, you hear the cooling system of the truck going up. So the AC compressor starts running. You also hear the fans of the truck, and that all ramps up until it reaches its maximum cooling capacity. So, and this is actually what you just heard, what I just played back, this last part. Good. So we also did measurements in the cabin to see what the driver is experiencing, and this is what's shown here in this graph. So first, you see the surrounding noise, and the cabin was actually quite well isolated, so you couldn't really hear much from this noise from the charging dispenser. So this first part of the measurement would be fine, not for sleeping, but for resting conditions. And when the driver would be sleeping, he would not be charging that fast. But then you would hear the run-up of the compressor and the fans, and I'll play back this short section, how that sounds in the cabin. Okay, so it would slowly ramp up until it finally reaches the maximum cooling capacity, and that sounded like this in the cabin. I'll spare you the rest, but you see that the levels, the 76 decibels, they are not exactly resting conditions. So there's a job to do. And if we want to look a bit deeper on what the contributing sources are, I've mentioned most of them already, but here are the measurements with the microphones outside of the truck. And during the first part, you see in the measurements mainly the first orders of the fans in the cooling of the cooling system of the dispenser, and then a broadband noise from the fans. And then, as soon as the cooling system of the truck starts, you have the first order of the truck cooling fans. It actually had two fans in the front. So if you look at it here at the top. In this picture on the top, you actually see that this order line is a bit dotted. So you had a beating effect of these two fans with the same blade numbers running at the same speed. And you also had a dominant first order of the compressor, and then all these multiple orders of the compressor together with a broadband wind noise from the truck fans. So this was the first part, this insight into the measurements we did. And what we then did is we took those measurements as an input for a noise map simulation. So if you were to build up a theoretical megawatt charging station. So we took a sample location near the German A9 Autobahn, and we actually modeled it as a noise map. So we took the background noise from the highway, which you can get from public databases, and we modeled the surrounding buildings with their reflective surfaces. And as you can see here in the picture, these small 5 white lines, those are the hypothetical 5 trucks charging in parallel at this charging station. And you also see that close by there are 2 hotels. So, right. So this is the background noise from the Autobahn that we took, the 5 trucks. And then if we take the data from the measurements that we took as an input to describe the trucks with 2 monopoles, one at the front and one on the side, with the calculated sound power from these measurements, you would see that the noise levels in front of these close by hotels, or like you can think of the typical Autobahn rest station with restaurants where people would want to sit outside, that increased the sound level by plus 10 dBA. Again, provided that the sources are like the trucks we have measured, these currently available electric trucks. And you can also see that the sound radiation goes mainly to the front of the trucks where the fans sit. So I'll get to some recommendations of how to do the layout of these charging stations at the end of the talk. But before we come to this, we also looked a bit deeper into the interior noise, so what the driver was hearing. And this was mainly due to the climate compressor. So here again, you have this interior noise measurement, and I'll play back this small portion of the sound for this maximum cooling rate of the truck. And I don't know if you ever worked on cooling systems, maybe also in the battery electric vehicles, you can already hear from the sound that this is mostly this scroll compressor. But we looked into it a bit deeper. So what you see here is the black curve is again the curve from the left side. This is the overall sound pressure level, and we did an order analysis with the orders of the compressor. And what you see here, that after the run-up of the compressor, which starts there at 350 seconds, the sum of the compressor orders, so that's the green line, is basically almost on top of the black line. So this is what I just said, right? If you listen to that, that's mainly this climate compressor. And if you then isolate only the first order of the compressor, then especially at this highest cooling rate here on the very right, it is actually dominated, so that the sound file that you just heard was dominantly produced by the first order of the compressor. So, I had a background in compressor noise, and I thought, okay, let's look a bit deeper into the truck that we have. So, for you to understand these compressors, first of all, I have a picture here of this compressor, how it was mounted. It was mounted rigidly to the ladder frame. And the working principle of these compressors is that you have 2 scrolls. One of them is standing still, and the other one is orbiting in the standstill scroll. So it's not rotating, but it's doing an eccentrical orbit, and thereby it is pushing forward a small volume of refrigerant to the middle, and thereby compressing the refrigerant fluid. But the important thing, if you want to model this dynamically, is that you have a certain unbalance that is needed. You cannot go below a certain unbalance, because this black part, it needs to be pressed against the standstill red part to ensure a pressure ceiling. So depending on the pressure you have, you need a certain minimum unbalance. So why did I say this? We wanted to investigate, is it the compressor or is it the truck that is the problem? So we investigated this a bit further. We knew from past experience that the compressor can be modeled just as a rigid body in this frequency range of the first order. That's 10 to 150 hertz approximately. And we did a blocked force analysis. So we computed the forces of this compressor and compared it to what we know where it should lie. So what we did is we took a 3D scan of the benchmark vehicle to come up with this rigid body description of the compressor. And we did a few impact measurements. You maybe can't see it that well, but there's small blue arrows here. So we had like 12 impact positions on this compressor. And then to describe it as a rigid body, we did a geometric reduction, a virtual point transformation with these impact measurements. So basically we had not the transfer function from our impact measurements to the sensors, but the transfer function from free forces and free moments in this virtual point to the accelerometers. And with that, we could compute the blocked forces. So here on the top right, you see the force of the first order of the compressor. So it goes up approximately quadratically with the speed. So the x-axis here is the rotational speed of the compressor, and the y-axis is the force. And from this curve, this is, I have to say this is the RMS value of the force in the x and y direction. So this is the direction in which this unbalance is acting of the compressor, this dominant first order force. And we could infer that the unbalance was around 80 gram millimeter for this compressor. So actually the component was fine, but we of course also had the transfer functions, and we could see that there's a very dominant peak, actually 2 modes in the system. And that was actually the issue with the sound file that I've just shown you. So if you look at the modal analysis here of this peak, you see that there is a mode which is also being excited by the unbalanced force in the x and y direction of the compressor. And then if you look at the operational deflection shapes of the compressor, it's virtually the same. So in this sound file that I've shown you, if you animate the vibration at the first order, that was at 137 hertz, and the mode was at 135 hertz, they are virtually indistinguishable. So that's just an example for why I think, and I wanted to have this presentation and this talk to tell you we need to consider this. And I think it's all technically solvable, but we shouldn't compromise on the public and acceptance of the drivers by not including it in the design criteria. So yeah, actually just before the talk, I made a small napkin calculation. I wanted to show this to you to see, is this going to stay a relevant topic for long-haul trucks? Because what we measured were these urban trucks. So we had trucks with around 350 kilowatt hours of capacity. We charged it at only 100 kilowatt. And that means for the individual battery cell that you have a C rate during charging of 0.28. And what we are interested in is the thermal power that's being generated due to the charging. And that is approximately, so let's say we call the thermal power Q, and that is proportional to the capacity of the battery, right? So if you charge double the battery size with the same C rate, you have double the heat generated. And it depends quadratically on the C rate with which you are charging, because this C rate basically determines the current that's going into the individual cell. And that increases the thermal power quadratically. So if we say we go to long-haul trucks, the capacities will go to probably 700 kilowatt hours. And in order to get these 400 kilometers range back in, let's say, half an hour, for the driver, you need megawatt charging, so 1,000 kilowatt charging power. And for the C rate, that would mean it goes to 1.43. This is by no means a problem. This is nothing crazy. I mean, compared to what a Porsche Taycan, for example, is doing fast charging. So that's doable for the batteries. But that means we will probably double the capacity, and we will have a 5-fold increase to the measurements we did in the C rate. And that would mean that the charging power for these long-haul trucks would increase by a factor of about 50 in the small napkin calculation. So you need a lot of cooling systems running at these megawatt charging stations. So the recommendation here, let's say, for the acoustic community to make this work, I think this is the part that we can do as a community, is to include this as a design criterion early in the development phase, do design studies, use maybe hybrid approaches with substructuring, and find out what are good isolation concepts for the compressors, where do we place all these cooling components, how do we isolate them. And for the charging stations, we found that it's important to consider how you lead the trucks into the charging station. So that the front of the trucks is not facing towards the hotel, but rather toward the highway. And then, of course, on the truck design side, you would need to do once you have a design that in principle works, you would need to do a proper target cascading down to the individual path, for the airborne path, for the structure-borne paths, and to your components. And you could think about optimizing the cabin isolation even further, such that the driver, because if you have a good truck, it doesn't mean that the neighboring truck of your competitor is good. So you might even want to prevent him from that noise during his rest. And as a last resort, if you still have problems late in the development phase, you can, of course, also play with the operational strategy of the compressor and fans and not run them into resonances like in the measurement that I've just shown you. And then for the charging stations, we know that there's a lot of effort. People are also looking into separating the cooling, getting that out of the dispenser and get that into a separate building, which is then supplying all the, let's say, 5 or 10 charging dispensers and water cooling. So, yeah, thank you for the attention. Sorry, I'm a bit over time. Don't want to compromise on your lunch break.
Anyway, thank you, Michael, for this presentation. Yeah, thank you for that very interesting presentation. And yeah, we see there are some challenges to overcome when we talk about charging, and especially megawatt charging. Yeah, the stage is open for questions. Are there questions in the audience?